The key concept to this chapter for nuclear physics is the understanding that mass and energy are equivalent. This is completely abstract and is incredibly difficult, all right, to grasp this. But for this chapter, know that there are instances, all right, and it's been shown through special relativity, but that there are times when mass will purely convert to energy. Okay, so let's talk about this using this equation here. All right, knowing that a proton, okay, has a certain mass, we want to determine how much energy would be released if the proton were completely converted into energy. So we begin with our mass of a proton, okay, which is equal to 1.673 times 10 to the negative 27 kilograms. We also know the speed of light, which is c, which is in this equation, 3 times 10 to the 8th meters per second. And so what we do here is we calculate the energy released, all right, using these two variables. And when you do that, we end up with this much energy. Okay? The next question is to convert it into electron volts and mega electron volts. So we start out with this answer, okay, and what we do, right, is use our conversion factor that 1.6 times 10 to the negative 19 joules equals 1 electron volt, and solve it that way. And I just realized something. In order for you to get these numbers here, I need to actually give you a more precise definition for C. So let me just go back here and do that. It's going to be 2.99792 times 10 to the 8th meters per second. All right, and so that's going to give you this energy here. And then when we get down here and we convert this, the more precise energy of the electron volt is actually 1.602176. All right, times 10 to the negative 19 joules. All right, and joules go away here, and what we end up with is 938 billion, 9.385 times 10 to the, or excuse me, 938 million, sorry. So anyways, times 10 to the 8th electron volts, and mega electron volts is 938.5. All right, so these are some important numbers. So we have a new unit of mass that we're going to be using now in this class. All right, let's see here. Let's get to that first. All right, so this new unit of mass, all right, is going to come from E equals mc squared. And what we actually end up with here, right, is m is equal to E divided by c squared. So the unit that we're going to be using here, okay, for energy is the electron volt. And if we just keep the c squared in the denominator, it's a unit of mass, okay? So more commonly, though, we're going to be working on the level of mega electron volts per c squared, okay? And just dividing by that c squared, if we calculate the energy, okay, in terms of electron volts, then we now have our mass if we just divide by c squared, okay? Which is just a very common way of expressing things. So, for example, when we studied in class 1 unified atomic mass unit, or 1/12 the mass of the carbon-12 atom, okay? So let's see here, I believe this is 1.6605 times 10 to the negative 27 kilograms, okay? When we do this conversion all the way through, okay, and what I mean by that is if we look at the energy level, okay, if we use this as our mass and use, let's see here, 2.99792 is our C, times 10 to the 8th, this thing squared, okay? What we end up with is this many joules of energy. Okay, and this ends up converting to 931.5 mega electron volts. Okay, so what we have now is a new unit conversion, which I showed you before. Now you know the definition that 1 unified atomic mass unit equals 931 mega electron volts per c squared. All right? So some practice questions with this here, okay? The rest mass of a proton is 938 megaelectronvolts per c². How much energy will be released if the proton will completely convert to energy? Knowing this, right, we can just plug it into E equals mc squared. And the nice thing is that our c squared just drops out. And we're left with the total energy of that proton. Again, doing this conversion from unified atomic mass units now, this is just a conversion problem, okay? So if I were to give it to you this way and you only knew this is how many U were in it, okay? We use this 931.5 mega electron volts per c squared per U, okay? The energy that would be released would then be 938 minus with, I think, mega electron volts per c squared. Excuse me, this is the mass, and we plug this in up here to find the energy and get along the same value. Okay? So that is the conversion between mass and energy. What this leads us to is the next page, okay, where we see that the total, all right, mass of a nucleus is always less than the sum of the masses of its nucleons. I already mentioned this, okay? So what this is saying is that the total energy of the nucleus, right, is less than the combined energy of the separated nucleons, all right? So what this means is that energy gets released, okay, when a nucleus is formed, all right? And we'll get into how that is with stars and other fusion processes. But when a nucleus breaks apart, okay, it then will actually release energy as well, depending on what process that is, okay? But the point is that it's always going to a more stable state, all right? And so the mass, the formula that you need here is that the mass of the individual nucleons, just a really long subscript on the right here, okay, is going to be equal to the mass of the nucleus plus the mass defect, okay, that missing mass. And so that mass defect or mass deficit, that's the difference between the mass of the nucleus and the sum of the individual nucleons, okay? That's the energy that's released, all right, when it's formed from its individual components. Just a few notes to make here, okay? Different nuclei have different binding energies, so as a trend, nuclei, all right, as the atomic number increases, nuclei have higher binding energies. And as atomic number increases, nuclei have higher binding energies, okay, per nucleon, until we get to iron and nickel. Okay? So I have some practice problems here I'm going to take you through in the next video.